Hey,
How's it going?
I'm doing well.
Good. All right, I'm just getting myself ready here and get going. One more second. Okay. So, last time was maybe our final session, at least for a little while, on using the sum check protocol to design efficient interactive proofs and snarks. So I think last time we specifically saw Clover and Spartan, which are sum check based snarks for Clover is described in the context of circuit sat, proving the prover knows a satisfying assignment to some arithmetic circuit. And Spartan we described in the context of R1CS, which we also talked about the relationship between R1CS and circuit sat, and how in a sense you can think of R1CS as a generalization of circuit sat. And Spartan is more general, kind of easily extends to handle constraints that are not just rank one. So that was the topic of last time. And today, I think we're going to cover Marlin. So Marlin is a snark for R1CS. It can also be extended like Spartan to go beyond rank one constraints, but nice and clean and simple to consider rank one. And this is based not on the sum check protocol, but on univariate polynomials, rather than multilinear or multivariate, and KZG commitments, which is one particular polynomial commitment scheme to commit to univariate polynomials. And as with pretty much all snarks based on univariate polynomials, somewhere in the proof system, there tends to be something called quotienting, which we've discussed very briefly, I think very early in this run of the reading group. And I'll go into some more detail today. And broadly speaking, like what is the trade-off between Marlin and something like Clover and Spartan? It's the following. So Marlin has lower verifier costs and shorter proofs. So in particular, if you use KZG commitments, the proofs are a constant number of group elements, say something like 10-ish cryptographic group elements, which would be, if group elements are 256 bits each, that would be something like a couple kilobytes for the proof. But on the downside, the prover is slower. So basically, better verifier, worse prover if you use Marlin versus using something like Clover or Spartan. High level, sort of easy to understand comparison there.
Just curious, what is the numbers on the other side? So you said like 10-ish group elements and 2 kilobytes for Marlin. For the others, what does that look like?
Yeah, great question. So in Spartan, basically there's going to be like one or two sum checks in the proofs. And that you're talking about, let's call it, if everything's optimized right and there's, I don't know, 30 rounds in the sum check, 2 times 30. So let's call it 60. So there's like, you can send as little as 2 field elements per round. I'll work this out pretty quickly. It won't take me too long per round. 30-ish rounds. And it might be, you can work over different fields, but I don't know. Let's sort of conservatively say a 256-bit field. So that would be 32 bytes per field element. So the sum check proofs, you're going to look at couple kilobytes. For sum check proofs.
So in this case, you had 60 elements. Is that right?
Yeah. Okay. Good point. So my math might be,
because in the other case, you had 10 elements and it became 2 kilobytes. Like, are they just much bigger groups?
Yeah. You know what? I made a math error here. This was, it was like 2000 bits, not bytes. Sorry about that. So
we can totally revisit this. We also don't need to do all the math now, but I think it's important to have these comparisons on it.
Yeah, for sure. So it's 32 bytes per group element, right? That's 256 bits, which is just a few hundred bytes. That seems a little low to me. So maybe like 300-ish bytes. Am I missing something? You can run into, there's a chance I'm missing some factors involving, so some of these group elements would be in the target group of a pairing friendly group, and those are going to be 4x bigger. So this is a little embarrassing. I'm getting my numbers off, but let me actually call it. So I just sort of know without doing the math that Marlin proof should be like something like 1 kilobyte to 2 kilobytes. I did make a mistake in the math, but I think that mistake is somewhat offset by different oversight, which is that some of the group elements are target group elements in a pairing friendly group, and those are 4 times bigger. So anyway, Marlin proofs call it like a couple kilobytes, something like that. Spartan proofs, 2 kilobytes does seem right for a couple of sum checks to me. Maybe that's a little bit optimistic, but certainly under 10 kilobytes for sure. 10 kilobytes is what you see from like GKR, which is calling sum check many times. And then there's one polynomial evaluation proof from whatever polynomial commitment scheme you use. And so this can vary widely by choice of polynomial commitment scheme, which is why I'm giving the 2 separate costs. The main point here is that the Spartan, needs a multilinear polynomial, and those evaluation proofs are always at least logarithmic in size, and so you're never going to get anything like 1 to 2 kilobyte proofs. So like bullet, if bullet proofs were your commitment scheme, that would be like 40 group elements. This would be in no pairings needed. So now it really is 40 times 32 bytes. And that can also be, this is looking like 1 to 2 kilobytes there. So you add it all up and let's call it, minimum 4 kilobytes total. But there are polynomial commitment schemes that one might use here that would cause the proofs to go much higher. So if you use like Binius or something as your commitment scheme, then Binius alone is going to give you like 100 kilobyte plus proofs. Okay, so anyway, so to summarize that discussion, please excuse my math errors, which are pretty embarrassing, but what we're going to see today, you can get down to like 2 kilobyte size proofs. But what we saw last time, like minimum is going to be like 4 kilobytes, which is really like might be a little optimistic even. And if you use other commitment schemes, it could be 100 kilobytes or more. Other questions? All right. And just worth mentioning briefly, these KZG commitments, which are key to getting like the really short proofs, They do involve a trusted setup. Some kind of ceremony that happens where if everyone who participated in the ceremony got together, each person has like some toxic waste, and if they kind of put all their toxic waste together, everyone who participated, they could break soundness of the snark, and quickly find convincing proofs of false statements. But one nice thing is that the trusted setup is like not circuit specific. So like growth 16, you have a different trusted setup every time you change the circuit set instance you care about. Something like Marlin, you also have a trusted setup due to the use of KZG commitments to keep the proofs nice and short. It's like you can run that trusted setup once and then, handle any circuit up to a certain size bound. Okay, so we're going to talk about Marlin today and how it works. And so we're only going to see univariate polynomials today. Any polynomial I write, it just has a single variable, unlike all this sum check protocol stuff where they're multivariate polynomials. And Marlin is, most cleanly described for R1CS, which recall, that is the problem where the prover claims to know a vector Z such that AZ entry-wise product BZ equals CZ, where let's say A, B, and C are public matrices. So that is both the verifier and the prover, somehow know these matrices. Let's not get into details of how these matrices are specified right now.
Professor, I had a quick question. So so you say that while talking about Marlin, you say that every element in the target group is going to be 4 times the size of the source group element. I'm assuming that's the sentence. Are you making this statement for any bilinear pairing based group, asymmetric ones?
Anything? Yeah. I think my understanding is for the pairing friendly groups people use in practice, there's 3 groups involved, G1, G2, and the target group GT. And I think G2 elements tend to be 2 times, bigger. So 2 times as many bits needed to specify a group element as G1 elements. And then GT elements are two times bigger than that, so 4 times bigger. And this is just in the weeds of how, what are these pairing friendly groups, which I normally try to avoid going into those details because we really can just treat these pairing friendly groups as black boxes, and we don't need to understand exactly what the groups are and how the pairings are computed. It's just not relevant. Does that clear things up at all?
But I believe that there exist groups where all 3 of these can be multiplicative cyclic groups of prime order. So it's the same dimension.
They all have size about, or can have size about 2 to the 256. But that doesn't mean that but only G1 elements are naturally represented with 256 bits. So the deal is, if it because GT has size 2 to the 256, information theoretically, if I can uniquely specify any GT element with 256 bits, but that doesn't mean that if I give you, 256 bit specifications of GT elements that you can quickly, compute their group product or whatever. So it's naturally, actually, I think GT elements, we're getting way into the weed, more in the weeds than I tend to go, so I could say something wrong here, but I think they're often in FP to the 12th or something. So actually, whereas G1 elements are in FP, something like that. And so, in fact, if you're like really naive about things, the GT elements would be 12 times bigger, but there's like some way to do partial compression of them, so that, that they're really only 4 times bigger. But if you try to go below 4 times bigger, then you run into this issue that, if I give you the bit representation of 2 group elements, you can't, do arithmetic on them quickly. Does that make sense?
So I understood that's a reason for practice and not a theoretical statement. Is that correct?
Yeah. So it's
Okay.
like, yeah. So I think like if you didn't if you were okay with the Marlin verifier running incredibly slowly, like really, terribly, I guess the proofs would not necessarily have to be two kilobytes, 1 to 2 kilobytes in size. Maybe they could be, more like, under half a kilobyte. But if you want the verifier to like run decently quickly, it's going to be the proofs are going to be bigger. And I'm just thinking off the top of my head, the KZG proofs, maybe they don't have target group elements in the proof. Maybe they don't, but they definitely have G2 elements in the proof. So that, anyway, yeah. So hopefully this discussion was not a waste of time, and apologies. It's, I don't have everything cached about, low level details of these groups. But yeah, well, roughly like, 1 kilobyte-ish proofs is the right ballpark for Marlin. And it's because there's, 10 to 15 group elements in the proof, and some of those group elements are not in G1, which makes them bigger in standard implementations of the groups.
And you also mentioned that like some other strategy always produces logarithmic proofs, which are, I assume, not going to be sort of small enough compared to things like Marlin.
Yeah, right. So anytime you use multilinear polynomials, you're going to get logarithmic size proofs. Both the sum check protocol is going to contribute, logarithmic field elements to the proof, and then the multilinear polynomial commitment scheme is going to contribute, a separate logarithmic number of field elements to the proof. And so whenever you have like those log costs, your proofs are going to be like in the kilobytes. Like multiple kilobytes, whereas something like Marlin or like Growth 16, which is, kind of shorter proofs than Marlin, but like in the not that much shorter, they can be like 1 kilobytes and even lower. Growth 16 is less than 1 kilobyte size proofs. So that's the right intuition. And then if you start using the GKR protocol, which calls sum check many times, your proofs might go from, a couple of kilobytes up to like, a dozen or 2 dozen or even, more than that kilobytes. That's, I think that's the rough, maybe it's worth writing this down. Like if you use KZG commitments and univariate techniques, you can hope for like 1 kilobyte or a handful of kilobytes and below. Also Growth 16 is very close to using KZG commitments, although not quite. If you kind of call sum check like once or twice, and you use like a logarithmic verifier cost polynomial commitment scheme, you can hope for a few kilobytes or so. I don't know, 4 kilobytes up, and many sum checks, call it like, couple dozen kilobytes. And then if you decide to use a hashing based commitment scheme, regardless of how many sum checks you have or univariate polynomials or what, like the commitment scheme is going to dominate the proof size, and now you're talking like roughly 100 kilobytes and up. And maybe you can dip below 100 kilobytes if there's a lot of recursion, so maybe a little lower with recursion, aggressive security assumptions, and things like that. So that this is like, ballpark, take it all with a grain of salt, because there could be fudge factors of up to like, a factor of 3 or something here. But this is roughly the orders of magnitude. Oops, sorry. You should expect for proof sizes here.
Nice, thanks.
Yeah. Okay. So back to R1CS. Feel free to interrupt with more questions. Yeah, so these are called the constraint matrices, A, B, and C. And I guess it tends to be easiest, I don't know, let's say that there are m constraints. So that means each of the matrices has m rows and n witness variables, which what that means is that the matrices have n columns, and z, which I call the R1CS witness vector, is in field to the n. Okay, and the prover's claiming to know a z such that AZ entry-wise product BZ equals CZ. Yeah, and that's the problem that Marlin solves. Okay, so as we'll see, it actually, Marlin sort of conceptually proceeds like closely analogously to Spartan, even though the underlying proof machinery is totally different and based on univariate rather than multilinear polynomials. So it's like you can think of Marlin as like a univariatization of Spartan, or you could think of Spartan as like a sum-checkization of Marlin. And again, that translates into different cost profiles, with the univariate stuff being optimized for the verifier but not the prover, and the multivariate sum-check stuff being optimized for the prover, but you get these bigger proofs here. Okay, so let's talk about how Marlin works. So let's let A be AZ, so little a be capital A times Z, little b equal capital B times C, little c equal capital C times Z. So the first thing that happens in Marlin is the prover KZG commits to what's called, like, you can call it the univariate low degree extensions of little a, little b, and little c. So let me call that A hat, B hat, and C hat. And what I mean here by univariate low degree extensions is, so remember, these vectors have length m. So, A is in field to the m, B is in field to the m, C is in field to the m. They have one entry per constraint. And so what these are, like, the A hat is the unique univariate polynomial of degree m minus 1, I guess m minus 1, such that A hat of I equals A sub I for all I in some interpolating set H, where H has size m. And moreover, just like so these univariate low degree extensions, A hat, B hat, C hat, like, the prover can compute like their coefficients in the standard monomial basis, which is the basis that KZG commitments kind of want you to use for univariate polynomials to commit to them. We haven't talked about how KZG commitments work. We'll do that in probably a month or something. In the standard monomial basis in time, like m log m or something like that. If H is a nice set, and so typically what H is it's the set. In practice, people typically set it to the set of, so let me say, for example, the set of mth roots of unity in the field that the R1CS is defined over. Okay, so by mth roots of unity, I mean H is like those field elements x, such that x to the m equals 1. Okay, and so these algorithms to compute the coefficients of these univariate low degree extensions, they use FFTs. The FFTs, like to deal with roots of unity. I'm not going to go into the details, but so people will choose the field so that this set of nth roots of unities exists, right? There are some fields. If the field has size p, this typically basically requires that m divides p minus 1. Okay, and so people will work over these fields so that m divides p minus 1, so that the prover can run these FFTs and stuff. Moreover, if you want to use KZG commitments, you'll also need p to be p being the size of the field, to be the order, the size of a pairing friendly group. Okay, and so that's why you see people use curves like BLS 12381 or BN254. They both have these nice properties. I think in BN254, m can be any power of 2 up to 2 to the 27, I think. So this is actually, I think this is probably not that widely known, that if you use BN254 as your elliptic curve group, that you run Marlin or Planck or Groth 16 over, I think you cannot handle more than 2 to the 27 constraints, no matter how big your trusted setup is. Another pain point is running people have run trusted setups of size 2 to the 27, letting you commit to vectors of length 2 to the 27. But the SRS is multiple gigabytes in size and things like that. I think BLS 12381, some even larger power of 2. I don't know quite how big it is. Maybe 2 to the 30 or something. I don't know offhand. Larger power of 2 divides p minus 1 for this curve. Anyway, so back to that was a little tangent about how because people want to interpolate with these roots of unity, that does place some restrictions on the kinds of fields you can use. But anyway, so A hat, B hat, and C hat, they are just the univariate polynomials that have the same behavior, kind of evaluate to the entries of A, B, and C respectively when you focus on their evaluations over the appropriate interpolating set. Okay, so the very first thing the prover does is just KZG commit to these univariate polynomials. Let me just pause here. Does anyone want to ask any questions about this first step of the protocol?
One question in the chat is, do R1 CS matrices always need to have a power of 2 number of rows?
Yes and no. The short answer is no, it's not really intrinsic to the proof machinery, but then the longer answer is it's in practice sort of yes, because people want to use these roots of unity and they sort of choose, it's nicest and easiest to choose fields where you're dealing with power of 2 size roots of unity. If you didn't want KZG commitments and you wanted to use Fry, that really okay. Let me just say, if you don't want powers of 2 number constraints, your life is going to get much, much, much harder in practice. Okay, but the reason your life is getting harder sort of feels like it's coming in from non-fundamental things, the people have carefully chosen certain fields and elliptic curve groups and stuff, for powers of 2. The sum check, even if you're using sum check based techniques, right? sum check, you typically have a giant sum over Boolean vectors, 0, 1 to the L for some L. And so your sum is like naturally always over 2 to the L terms there. So you have powers of 2 coming in there as well. But there, you're not going to need FFTs necessarily. Also, you can often kind of, if you have a non-power of 2 number of constraints, it's like you can often just pad the constraints with, kind of nonsense, automatically satisfied constraints to get a power of 2 number of constraints and like not really wind up paying for the padding anywhere seriously in the protocol. So apologies for kind of the wishy-washy answer. I guess I should just leave it as life is much easier if you have a power of 2 number of constraints. If you're willing to suffer enough, you might be able to avoid that. Okay, other questions?
Yeah, coming.
Okay, great. Yeah, like we're dealing with some of the stuff in Jolt now where like, like in Jolt, we run like 100.
Quick question, Professor.
Yeah, I'll just finish this sentence and then go
Sorry,
ahead. So,
sorry.
yeah, in Jolt, we have like 110 grand products, right? And life gets much easier, would be much easier if we had 128 of them, right? Because that's a power of 2. And so, we're dealing with that now. We're kind of implementing how to deal with that right now. And the way I'm planning to do it is to just add in an extra 18 grand products that are kind of trivial. And I don't think that this should increase the prover time. Like, firstly, even if you do kind of pay for the padding, it's only like an extra, 18%. But on top of that, because the extra grand products we're putting in so that there's a nice power of 2 number of them are sort of trivial, they really shouldn't cost anything at all. But making sure that they really cost nothing is an engineering headache that we'll have to suffer through. So anyway, go on with the next question, please.
Yeah, sorry about that, sir. First of all, my apologies to the practical people here, but I just wanted to put this in the same frame. So, till last class, we were talking about sum check based protocol, and the proof size analysis was being stated asymptotically in the circuit size.
Mm-hmm.
So, would it be possible? So, I understand that right now we are talking about concrete proof size analysis. Kudos to that. But would it be possible to paint this topic of today with R1CS's topic, the analysis of that proof size with respect to asymptotic analysis with respect to the circuit size?
Great. Yeah. So, so last week I said, like the Spartan, or Clover proofs, if you want to talk about, let's talk about circuit size. So Clover. So they were logarithmically many field elements. So log circuit size field elements. Plus like one polynomial evaluation proof for whatever multilinear polynomial commitment scheme you wanted. And again, we haven't talked about the details of polynomial commitment schemes. That's kind of the next big topic we get to, and maybe ZK first, because it's the polynomial commitment schemes kind of build on the same technology as how you achieve zero knowledge. But yeah, so just treat it as a black box. Like, here's some polynomial evaluation scheme, and we're going to have one evaluation query to commit a polynomial. Today, it's going to be, I guess, order 1, like group and/or field elements, plus, let's say, order 1 polynomial evaluation proofs. But now we get to use a univariate polynomial commitment. The reason I highlight that is the univariate schemes like KZG commitments can have, which themselves can be, order 1 group elements. So everything today is order 1. The number of group elements and field elements, like from other than the polynomial evaluation proofs, is all order 1, and then the polynomial evaluation proofs themselves, there's constantly many of them, and each one is constant size. And the only reason we're able to get constant size is because of univariate polynomials being used. So that's the difference. So, again, there are some commitment schemes that are quite popular today, these hashing-based ones, where the real bottleneck in proof size is the evaluation proof, and then you can ignore everything but that. But if you use a polynomial commitment scheme that's not hashing based, these evaluation proofs can be very short, and then you do kind of have to pay attention to all of the costs I just listed here to understand the total proof size. And then the difference asymptotically is kind of logarithmic from last week versus constant this week. Is that a brief enough, clear enough, helpful explanation?
Yes, sir. Thank you.
Great. Any other questions? Okay. All right. So back to Marlin. So remember, like little a was a times z, little b was b times z, little c was c times z, and then the first thing that happens in Marlin is the prover, KZG commits to a hat, b hat, c hat, which are their univariate low degree extensions. Okay. And so now at this point, the prover wants to prove that for each constraint I, it is the case that a hat I times b hat I equals c hat I. So another way of writing that is minus c hat I equals 0. Because this is what this by definition of R1CS, this is the ith constraint. Right. Like, if you look at what, R1CS is saying, it's saying, little a entry-wise product, little b equals little c, which that's just what I wrote here, entry by entry. Yeah. So that's one thing the prover wants to prove. The other thing the prover wants to prove is that indeed, little a equals a times z, little b equals b times z, and little c equals c times z. Right. So I kind of overloaded notation here where, if the prover is on, so the prover commits to some polynomials. If the prover is honest, the first committed polynomial is the univariate low degree extension of AZ. The second committed polynomial is the univariate extension of BZ and so forth. But if the prover is dishonest, it might have just committed to other polynomials that are not. So that's what this 2 is. So. And ensuring, like the prover committed, to the vectors, or it was supposed to, and not some other vectors. Right. Like obviously, if you don't have this second check in here, then it could just commit to, 3 vectors that do satisfy these constraints, but just have nothing to do with z. So these are the 2 things that need to be checked. Okay, any questions about the 2 things that need to be checked at this point?
One question. It says, is it for all I in H?
Yes. Yes. For all I and H, and that's like we're just thinking of. So it's like we're just thinking of the constraint, like the entries of A, B, and C, and there's one entry in each of them per constraint. We're thinking of the constraints as being indexed by H elements. If there are M constraints, well, there's also M elements of capital H, and we're just, using any sort of bijection between the 2. This is completely analogous to how, when we have some check-based snarks, and we have a vector of length m, we consider sort of log m bit labels for the entries of the vector. So it's like in some check-based snarks, you'll label entries of a, b, and c by bit vectors, log m bit vectors, meaning in 0, 1 to the log m bit strings. But here in univariate based snarks, like Marlin, Gross 16, what people call Starks, you'll basically always label the entries of vectors by roots of unity. So if your vector has length m, you'll be dealing with mth roots of unity because there'll be m of them. So you can, kind of treat, label the ith entry of the length m vector with, the ith mth root of unity. Did that answer the question? Was that clear? So this is just saying for every constraint in the R1CS, the constraint actually holds. And then, this is saying that the vectors that were actually checked above indeed have the correct relationship to the solution. By the way, I guess I forgot to say I forgot to say that the prover also at the very start has to commit to z hat as well. So all four of these get committed at the very start. Okay. More questions? All right. So then let's start with how the prover proves one. Right. So again, A hat, B hat, and C hat are committed, and it wants to prove that, for every one of the m entries of H, this equality holds. Okay. And so in univariate snarks, so this is completely analogous to, last week with Spartan, we saw this was checked with a single application of sum check last week. And I think I mentioned that people will call it they'll call that the zero check PIOP. And it's just H there again was 0, 1 to the log m or something rather than mth root to unity in a field. Today with univariate snarks, this is checked with what's called people call it the vanishing argument. I would call it quotienting. Okay, but here's it's a fact. So let's see, let G of t equal A hat of t times B hat of t minus C hat of t. And note that the degree of G is at most 2m, right? Because A, B, and C hat, A hat, B hat, C hat each have degree m. So when I multiply, two of them together, I get degree 2m at most. And so the fact is that G of I equals 0 for all m through to unit for all I in H, if and only if G is divisible by what's called the vanishing polynomial for H. Let me define that. So this is the vanishing polynomial for H is the unique degree m polynomial. I'll call it bold Z sub H, such that bold Z sub H of T equals 0 for all, or maybe I could say of I equals 0 for all I in H. So it kills everything in H and nothing else in the field. And so if H equals the nth root to unity, so if H is X in the field such that X to the M equals 1, then the vanishing polynomial for H is just T to the M minus 1, right? Because by definition, nth root to unity are exactly those field elements that this polynomial sends to 0. Okay, and so I don't want to spend too much time proving this fact, but one direction is obvious anyway. So I'll just sketch. Maybe I'll only prove the easy direction. So if G is divisible by H, that means you can write it as Q of T times the vanishing polynomial. So if G is divisible by the vanishing polynomial, where this Q would be like degree at most M, because ZH has degree exactly M, and G has degree at most 2M, and then clearly, so this is the easy direction, G of I does equal 0 for all I in H, because G of I, by this equality up here, star, is equal to Q of I times the vanishing polynomial at I, which by definition is 0. Just because the vanishing polynomial evaluated at anything in H is 0. And then so the reverse implication is also true, that if G does vanish on H, meaning G of I is 0 for all I in H, then in fact you can give there is some quotient polynomial Q such that G equals Q times ZH. Okay, does anyone want to ask any questions about that fact?
There was another question in the chat, which was so the roots of unity that you were talking about, are they from the base field of the elliptic curve group?
They are from the scalar field.
Okay, yeah. What is the distinction?
Good. Okay, so it helps to talk about to say a little bit about how the commitment scheme, how these curve-based commitment schemes work for a second. So KZG commitments, I'm going to just tell you briefly how they work. Otherwise, I don't think it's going to make much sense telling you the distinction. It'll just be some technical answer that doesn't really connect to the proof system we're discussing. So, and by the way, the same thing, everything I'm about to say really also applies to, bullet proofs, like anything that uses curves. So it's not really specific to KZG. If you want to commit to like a polynomial A hat, let A be the vector of coefficients. So let's say this is degree M. Let A be the vector of M coefficients of A hat. And the commitment to A will be the following. Okay. Let me say, okay. So before I tell you what the commitment is, the commitment scheme involves what's called a proving key or committing key let's say it's A hat is degree M minus 1, so there are M coefficients. So there'll be a proving key of M group elements. Okay, G1 to GM, or let's say G0 to GM minus 1. Okay, and the commitment to A, now, we can either treat the group operation, we can call it addition, or we can call it multiplication. If you call it addition, it would just be the inner product of the vector to be committed and the vector of group elements that is the commitment key. So another way of writing that would be sum over I equals 0 to M minus 1 of AI times GI. This is if this sum is group sum, if it's an additive group. Okay. And if it's a multiplicative group, this would be, this would instead be what's called a multi-exponentiation product from I equals 0 to M minus 1. You would be sticking the AIs, the entries of A in the exponent. It's literally the same like everything I wrote here is the same. The question is just, do you denote the group operation as addition or multiplication? Let's call it addition for now. Okay, and so addition for now. So yeah, so in order for this to make sense, though, so remember, AI is a field element, and GI is a group element. Okay, so in order for it to make sense to multiply this field element by this group element, it's necessary for AI to be in the scalar field of the group. Okay.
Yes, I guess the question is, isn't that the only field involved?
Right.
Because we were talking about base field versus scalar field. Are there multiple fields?
Great. So if you treat the elliptic curve group as a black box and you never ask like what is a group element, okay, you will never encounter the base field. You will only ever encounter the scalar field. Okay, so
the base field is like the elliptic curve group is made up of a bunch of XY pairs that have to like satisfy an equation, and those X and Y are coming from the base field.
Exactly.
And the two do not have to be the same.
They're not,
the base field of the. Okay.
And in fact, if the base field equals the scalar field, if they're the same field, then discrete logs are easy to compute in the group. And so it's not secure to use that group. So what that means is the base field, in cryptography is literally never the same as the scalar field. Yeah. So sorry for the long-winded answer to your question. So yeah, I like to think of like the values being committed by your commitment scheme. I prefer multiplicative groups in most contexts. I think I'm an outlier there. And so the reason I prefer that is because you can talk about, sticking like the values you want to commit in the exponent. You think about like hiding them in the exponent, right? If I give you GI to the AI and discrete logs are hard to compute, it's like it should be hard for you to figure out AI given GI to the AI. So you've kind of hidden AI in the exponent of GI. And so, yeah, in order to commit to a vector of field elements, like these curve-based commitment schemes, just stick those field elements in the exponent of group elements. And for that to make sense, like the possible exponents, the space of possible exponents is what's called the scalar field of the group. And so, yeah, the vectors you want to commit, these field elements come from the scalar field. But then the group elements themselves are pairs of base field elements, and they're different fields. And so life gets very confusing when you start, actually paying attention to what the group elements actually are. You start talking about a completely different field. Okay, should I say anything else on this topic?
Made a lot of sense.
Okay, good, thanks. Sorry as always for the tangent. Okay, other questions? All right. So yeah. So remember, at this point in the protocol, the prover committed to Z hat, A hat, B hat, C hat, and it wants to prove that every constraint is satisfied by the ABCs, and also prove that the ABCs are correctly related as they should be to Z. So to prove that the constraints are satisfied, I gave this little fact which says all the constraints are satisfied, entry-wise by A, B, and C, if and only if this polynomial G, which is just A hat times B hat minus C hat, is divisible by the vanishing polynomial for the roots of unity. And so what the prover will do is, so to prove one, which was that A hat of I times B hat of I minus C hat of I equals 0 for all I and H, the prover will KZG commit to Q, the quotient polynomial, where Q is such that G of T, which remember was A hat of T times B hat of T minus C hat of T, equals Q of T times the vanishing polynomial of T. And so now the verifier, so the verifier wants to, let me call this star star. V needs to check that star star holds. And the way it does it is V picks a random field element and confirms that G of R equals Q of R times the vanishing polynomial at R. Okay, and so where is it going? How is it going to get these three evaluations? Well, remember the prover committed to Q of R with a polynomial commitment scheme, so Q of R can just come from an evaluation proof. So this evaluation, comes, from the commitment scheme. Like that's the whole point of a polynomial commitment scheme, is the prover. It lets the prover commit to Q, and then after the Q is committed, the verifier picks the R at random and says, "Hey, tell me the committed polynomial at R." And KCG commitments lets the prover provide that evaluation and prove that the evaluation indeed is consistent with the committed thing. And similarly, G of R is A hat of R times B hat of R minus C hat of R. And A, B, and A hat, B hat, C hat were committed with KZG commitments. So each of these can also be had from the commitment scheme, one evaluation. And moreover, so we have 4 different committed polynomials, each getting evaluated at the same point R, and there's certain batching techniques you can do so that you don't really pay for 4 separate evaluation proofs. You can kind of produce just one evaluation proof that sort of proves all 4 queries at once. And then ZH of R is just R to the m minus 1. And so the verifier can compute this on its own in log m time, log m field ops. Okay, and that's yet another reason why roots of unity is a nice interpolating set for these univariate snarks, because typically the verifier will have to evaluate the vanishing polynomial for the interpolating set at a random point, and roots of unity have this nice sparse vanishing polynomial where there's just two terms in it, and so that the vanishing polynomial is very high degree. It has degree equal to the number of constraints, but it can nonetheless be evaluated in log m time, logarithmic in the number of constraints. So that is how the first check is done in Marlin, confirming that indeed A hat of I times B hat of I minus C hat of I equals 0 for all I. And by the way, like I didn't, the reason it's okay, it's sound for the verifier to just check star star at a random point is just the standard fact that any 2 distinct low degree polynomials can agree on at most, like degree many points, right? So if it's not the case that G equals Q times, the vanishing polynomial, right, then these are G is degree 2m, Q times the vanishing polynomial is degree 2m. So, if the probability over the random choice of R, if G does not equal Q times the vanishing polynomial, this probability that G of R would equal Q of R times the vanishing polynomial at R would be at most like 2m over field size. And remember, since we were working over a field of size 2 to the 256 anyway, just because that's how big the field needs to be to use KZG commitments. So this probability is tiny, tiny, tiny. So if it holds at R, if this equality holds at R, the verifier can be very confident that in fact G is the same polynomial as Q times ZH as the prover is claiming. Okay, questions about that?
Yeah, there's a question here that I'm not sure I understand, so hopefully you will. The question says, how can we check if G actually is A of R times B of R minus C of R, otherwise the prover could just multiply a random polynomial with the vanishing polynomial and get a valid G.
Great. So it's implicitly checked because G is never committed directly, right? What's happened when I say the verifier evaluates G of R, what it really does is it evaluates A hat of R, B hat of R, and C hat of R, and computes, the first evaluation times the second evaluation minus the third evaluation. And so that's just forcing G to be A hat times B hat minus C hat. So I was just using G as a shorthand, really, for A hat times B hat minus C hat, so I didn't have to keep writing A hat times B hat minus C hat. So you would absolutely have to worry if like G was specified via separate commitments. You would then need a separate check to confirm that the committed polynomial G in fact does equal A hat times B hat minus C hat, but really G is just a shorthand for A hat times B hat minus C hat. Did that clear things up?
It sounds like that's just a definition you're introducing here for notation.
Yeah, it's just for notation, exactly. So if and in particular, like if you are worried about like what the verifier's check really is this. So the verifier picks a random R and checks that A hat of R times B hat of R minus C hat of R equals Q of R times the vanishing polynomial at R. Now there's no G anywhere, right? G was just a shorthand for A hat times B hat minus C hat.
Yeah, we're good.
Now, you can ask, maybe a related question is, how do you know that all of these committed polynomials actually have degree at most m, and therefore that, this G, which is a shorthand for A hat times B hat minus C hat, has degree at most 2m, and therefore this like soundness analysis here holds? And the answer is that's promised by the polynomial commitment scheme. So, the polynomial commitment scheme, the cryptography within it, inside of it, is guaranteeing that, if the prover is able to produce a convincing evaluation proof, then indeed A hat of R is in fact, some degree M polynomial A hat evaluated at R thing. So the degree bounds are getting enforced by the polynomial commitment scheme, and my analysis here can just sort of assume that everything, all of the polynomials arising have this degree bounds as a result. Okay. Other questions?
That looks like it for now.
Great. Okay. So, let's see. So now we're still left with checking that A hat, little a equals AZ, little b equals BZ, and little c equals CZ. Let me just focus on the first one since they all can get checked in analogous manner. Okay, so let's see. Now I'm slightly regretting that I overloaded notation with A hat being like the thing the prover actually committed to, as well as the multilinear extension or the univariate extension of like what the prover should have committed to. So okay, so let's let A star. Do I want A? That notation's pretty bad. Let me just think for a second. Good notation. Okay, so let's let A hat be what the possibly dishonest prover committed to. And S be AZ. So this is S hat be AZ hat. So this is what the honest prover would have committed to. What the honest prover commits to. Okay. So now what the prover is really trying to show, to be precise here, is that so P wants to establish that the polynomial A hat he actually committed to is the same polynomial that he should have committed to. Yeah, that they're the same polynomial. Okay, and so how is the verifier going to check this? the verifier, as usual, is going to pick an R at random. Let me say R prime, I don't know, from the field, and we'll check that. Once to check, because I'm going to have to explain how. Once to check that A hat of R prime equals S hat of R prime. And again, this is secure because if A hat and S hat are not the same polynomial, they both have degree m, and so the probability that they agree at a randomly chosen point is at most m over the size of the field, which is tiny because the field is size 2 to 256. So yeah, we get to, rather than checking that they're the same polynomial kind of as a whole object, it's kind of enough to just check the equality at one evaluation, at one randomly chosen point. Okay, and now again, the verifier can get the evaluation A hat of R prime, from the KZG commitment to A hat. Right. That's what KZG commitments are designed to do, is to let the verifier say, hey, I want to know the committed polynomial evaluated at this point that I picked. Tell me, along with the proof that you're really being honest when you give me the evaluation. And so that's where the verifier gets the evaluation of A hat. But the big problem is the verifier doesn't know S, right? S is the univariate low degree extension of A times Z. Z itself is only committed, or more precisely, Z hat is committed. So the verifier doesn't know what S hat is. How's it going to get S hat of R prime? Okay, and fortunately now we have another fact, okay, which is that S hat of R prime is the same as the following. So, okay, this is going to involve a certain bivariate polynomial that I guess I haven't defined yet, but hopefully it will intuitively be obvious what it is. So S hat of R prime is the same as the sum over constraints. Remember, and constraints are indexed by mth root to unity. Okay, of capital A hat. This is the bivariate thing I haven't defined yet, but it should be pretty clear what it is. I'll tell you in a second the details of R prime. Sorry, hold on. Let me. R prime is sort of like a random constraint. Okay. Sorry. Okay, so assume for a second. Assume that the number of rows and the number of columns of the matrices are the same, so that columns, can also be indexed by mth root to unity elements of H, the same as the rows were. Now, if that wasn't the case, it's no problem. You just needed to index columns by nth root to unity rather than mth root to unity. But it's, rather than introducing a new notation for the nth root to unity, let's just assume m equals n. And so, indexing the rows and indexing the columns, you can index them in the exact same way. So this is summing over columns. And so it's sort of like we're sort of, this is loosely analogous to picking a random constraint, except it's not a random constraint because R prime is in the whole field. Not necessarily, or probably almost certainly not in H. Okay, so if R prime were in H, R prime would be, you would think of it as like a random constraint, but it's from the whole field, so it's not really, anyway. So it's like we're fixing the constraint to R prime, whatever that means, given that R prime is from the whole field. And then we're summing over, after fixing that constraint, we're just looking at that constraint. Or like we're looking at that constrainted entry of S. So anyway, so the fact is that S hat at R prime is this sum over columns of A hat of R prime, the jth entry of A hat of R prime times Z hat of J. Okay, so that's the fact. Proof, this is an easy proof. It's completely analogous to, when I say, hey, some multilinear extension equals some weird expression that's some check friendly, we always check two things. We would check that the right-hand side is multilinear. Now, today we're not dealing with multilinear polynomials, we're dealing with univariate. So the analogy is check that the right-hand side. So this sum is of degree at most m in R prime, and check that the right-hand side has the appropriate evaluation behavior over the interpolating set, which, today is H rather than 0, 1 to the L for some L if we were dealing with sum check. Okay. And so that is, so yeah. So let's check these two things. Now, okay, I guess I have to tell you what A hat is. Okay, so this is the unique bivariate polynomial such that, of degree at most m in each variable, really m in the first variable, n in the second variable, but I'm assuming m, the m and n are the same, such that, a hat of I comma j equals aij for all ij and h. Right. So it's the unique, it's treating A as a bivariate polynomial, right? It's the unique bivariate low degree extension of A. Okay. And so because A hat has degree at most m in each variable, and R prime is only fed into A hat, like clearly the right-hand side is a degree m polynomial in R prime. Yeah, does anyone want to ask any questions about that? Like basically, if you just look at one term of the sum, you get, so fixed j, a hat of R prime comma j times z hat of j, that is just a degree m polynomial in R prime because a hat has degree m in each of its two variables, in particular in the first one. Okay, and then so if I sum over all j, I'm just summing up a whole bunch of degree m polynomials. It's still degree m. So great. So the right-hand side has degree m in R prime. And as I was babbling before, like if R prime is actually an H, so it's it's like indexing a constraint, then what the right-hand side spits out is, is just the definition of the R prime's entry of AZ. So the right-hand side evaluated at R prime, if R prime is indexing a constraint, so it's an H, is just the R prime's entry of AZ, right? Because that's sum over columns J of A of A of R prime comma J times ZJ, and that's exactly what this sum is giving. Okay, so again. Marlin, I view it as just like a univariatization of Spartan. And similarly, Spartan is a multilinearization, sum checkization of Marlin. The two works were done roughly contemporaneously. And I don't think people realize that they were basically the same things, up to vast differences in the underlying proof machinery, quotienting versus sum check, for a while. Anyway, but this is the key fact. Okay, so I gave a nice expression for what S hat of R prime, and so now the question is, how is the verifier going to compute the right hand side here? So as a result, the verifier needs to know S hat of R prime, which the fact just told us that was sum over columns J, or columns, so J and H of A hat of R prime comma J times Z hat of J. Okay. And actually, let me remind myself how this is going.
Question, Professor, before
Yeah.
we go deep.
Go ahead.
So maybe one link, and that is, I feel a little bit missing for me, is that given that the high level functionality is the same, with
Mhm.
respect to what was being talked about last day and today. So last day, Emily was including a gate by gate check of the circuit, right? But
Mhm.
today you're fixing one constraint and you're checking that particular constraint. So would it be possible to make one link between the two computational models at a high level?
Well, I would say last week what happened was the way to answer this is to give a brief recap of what happened last week. So now when we talk about last week we talked about arithmetic circuit set and R1CS. Today we're just talking about R1CS. So I guess it'd be cleanest if I recap last week talking about R1CS. So last week the prover never commit to the multilinear extensions ABC. So they weren't committed. But let's ignore that for a second. But the verifier nonetheless wanted to check last week that a twiddle of I times b twiddle of I minus c twiddle of I equals 0 for all I in 0, 1 to the log m. Again, today the analog of 0, 1 to the log m is h, the m through to unity. And again, it's just the difference, like univariate things like m through to unity, multilinear things like bit vectors. That's all. Different indices. And so the way we did that was this was equivalent to checking. So today we used a fact about quotienting, right? We said this sort of thing held if and only if this polynomial was divisible by the vanishing polynomial for h. The difference last week was we didn't go through any quotient polynomial. Instead, we said these constraints hold if and only if if the verifier picks an R at random from field to the log m and checks that sum over I in 0, 1 to the log m of EQ R comma I times A twiddle I times B twiddle I minus C twiddle I checks that this whole sum is 0. So this is really just how they differed. Was today, we turned this sort of constraint check into quotienting. So we said that all the constraints were satisfied if and only if some kind of polynomial division relationship held. Whereas last week it was about just some big sum equaling 0. Okay, and then we applied sum check to this. Okay, last week. And at the end of sum check, the verifier, to check this, at the end of sum check, the verifier needed to evaluate the polynomial being summed at a random point, and that required needing a twiddle of R, b twiddle of R, and c twiddle of R. Let me actually call it R prime for consistency with this week at a random point. But here I really mean like the true, by a twiddle I really mean what I'm calling s twiddle or s hat this week. Like I mean like the true a, the true ABC, what the honest prover would send. And so in Spartan there would be a second sum check. Okay, now I mentioned at the very end last week that if the constraint system you're dealing with has a lot of repeated structure, you can cut out one of the two sum checks. Let's ignore that. So this is completely analogous to how there's two different checks this week too. This second sum check to compute, a twiddle of R, b twiddle of R, c twiddle of R is completely analogous to what we're talking about here about trying to get s hat of R prime. This is so it's like the first thing we checked with the quotienting is analogous to what the first sum check in Spartan is used to check. And the second thing we're trying to check now, the computation of S hat of R prime, is completely analogous to what the second sum check in Spartan is used to check. So with apologies for that lengthy comparison and overview, the summary is like everything is analogous, everything, but for the fact that this week, because we're dealing with univariate polynomials, the constraint checking was done with quotienting, and whereas last week it was done with one application of sum check. Okay, and so this is exactly. I'm really glad you asked. This is exactly like the comparison between all these univariate techniques that like almost every deployed snark today use, and the sum check techniques that I'm trying to convince people to use instead. Okay, the benefits for the prover of the sum check things are twofold. Okay, one is with sum check, the prover never had to commit to like little a, little b, little c, or the quotients. So there's less commitment costs. The other thing is the prover with the sum check never had to even compute the quotient. So those seem to be the two main benefits. So the prover commits to less data, and also some of the data that the prover has to, some of the extra data the prover has to commit to with the univariate stuff, these quotient polynomials, is just like pretty expensive to compute. And people have come up with tricks to kind of mitigate it, but they're only sort of partially mitigating the expense and stuff. And this is all why sum check based snarks are like generally better for the prover. On the downside, they're worse for the verifier in the sense that, like as we discussed at the start of today's session, you'll never get down to like under a kilobyte size proofs with the sum check based things unless you bring in, snark composition. Yeah. Did that answer the question? Did that clear things up?
Just see once whether I got what you're saying. So the computational model to visualize is the same gate by gate evaluation as it was happening last week. It's just additionally at each gate you're just performing a quotienting over the field.
Yeah, exactly. I guess I'd say the way you wind up checking the gate by gate claim today is with quotienting, that is univariate polynomial division property, whereas last week it was with one application of sum check. That's the only difference. Yeah, so today it's quotienting, last week it was sum check. That's otherwise these snarks, Marlin and Spartan, are like basically doing the same thing. Okay, other questions?
How do we get around different fields for the scalar and base field when using snark composition?
Oh boy, yeah. So that's just like a headache that. Here's the answer.
Can you explain the question a little bit? Like,
Sure.
why is this the thing we're talking about in the first place?
Yeah, great. Okay. All right. So, let's say I have an R1CS or circuit sat instance over some field F. Okay. As part of my snark for R1CS, if I'm using curve-based commitments, whether it's KZG, bullet proofs, it doesn't matter if it's multilinear or univariate, as long as it's using curves. So to use elliptic curves, ECs, elliptic curves, to commit to, Z, like the witness Z, or some extension of Z, whether it's more Z hat, Z tilde, multilinear, univariate extension, whatever. Remember, I need a curve whose scalar field is F, right? And that's because I'm going to be taking entries of my witness, which are elements of F, and like treating them as exponents of group elements. If it's a multiplicative group, kind of sticking them in the exponent of group elements, or if it's an additive group, they'd be like scalars, which is exactly why it's called scalar field. That terminology is kind of referring to treating the group operation as addition rather than multiplication. Otherwise, it kind of be called the exponent field or something. Okay, but then the verifier of my snark now is going to wind up doing group operations. Okay, and that involves operations in the base field of the elliptic curve group, right? Because remember, curve elements are pairs of, so the curve is pairs of base field elements. And so, like, you know, if I need to, let's treat the operation as the group operation as like addition. You know, if I need to, if like, you know, Y and I don't know, A and B are group elements. Sorry, are base field elements. You know, like A, B, and C, D. Let's say these are two group elements. Like computing the sum, the group sum of A, B, and C, D. Is going to involve, you know, like involves 6 to 12, you know, base field ops, right? So, you know, you need to, I don't even know what they are offhand. Like, you need to somehow, like, you know, add A and C and multiply B and D. I mean, I have no idea really, but, you know, these are base field elements. So naturally, you know, anyway, it naturally involves operations over the base field, which means, you know, if I want to do snark recursion, snark composition, what I need to do is I need to take the snark verifier and turn it into a circuit or constraint system, so that I can then apply. So this is for snark composition. This is what snark composition does. So that I can then apply a snark for circuit set, or, you know, or R1CS or whatever, to prove I know a proof that the original verifier would have accepted. Okay, so now we have the problem. The problem is, right, the snark verifier for the snark we start with needs to do operations over the base field. Okay, but like this was a snark for an R1CS or circuit instance over the scalar field. So now we have a problem, right? Like, like it's most natural to turn the snark verifier into a circuit over the base field. Okay, but then we'd have to, you know, be prepared to prove statements about circuits or R1CS defined over the base field, not the scalar field. Okay, that's the problem. Okay, and so what people do is twofold. So one thing you could do is just do what's called, so you pay in the constraints in the circuit representing the verifier, representing the first snark's verifier, to do, you know, like wrong field arithmetic, which is sort of the same as just doing like really big, you know, big int arithmetic, right? And this means, you know, if I want to represent, you know, operations in one 256-bit prime field, and represent that in a circuit over a different 256-bit prime field, like I basically, the best way we know how to do that roughly is to just have the prover provide as untrusted advice, like the bit decomposition of the numbers you want to add, you want to add, the big ints you want to add, and then you just like do the addition or the operation in binary, which is just like 1,000 times worse than if you could just natively do the operation with like one field op. So this is like you know, like one 256-bit, you know, field op turns into many thousands of constraints. Okay. But it's like, okay, many like a couple thousand constraints or something. If you're only doing a couple like wrong field ops, it's not a big deal, right? Like we can, a circuit with like a million constraints is not a huge deal. So like that means you can do several thousand like wrong field arithmetic ops in a circuit, and like you're not totally toast. Okay, but there are contexts where like this verifier that you're trying to turn into a circuit actually does many field ops, way more than like 1,000 of them or something. And then you really can't pay for wrong field arithmetic. And so then what people will look for is what you'll call like cycles of elliptic curves or something. You don't if you whether or not you really need a cycle depends on how deep your snark recursion is. But basically, a cycle of curves, the ideal situation would be you have two curves, G and G prime, where the base field of G is the same as the scalar field of G prime, and vice versa. The scalar field of G is the base field of G prime. Okay, and in this situation, you're sort of good to go. What happens there, and I'll say this sentence and then stop babbling, is, you take your first snark where the R1CS is over like the scalar field of G, and that snark verifier needs to do ops over the base field of G. And then you take that verifier and you turn it into a circuit over the base field of G, which is the same as the scalar field of G prime. And so when you go to, it's okay, like you're able to prove that you evaluated that circuit correctly by switching over to the other curve. And now when you need to commit to, the proof that verifier accepted or whatever, now the commitment works over G prime, and everything works out, right? Because the scalar field of G prime is the base field of G. The verifier of that snark needs to do operations over the base field of G prime. And so you turn that verifier into a circuit over the base field of G prime, and then commit to it using a commitment scheme, over G. And you just go back and forth every time you do another layer of composition where you prove a proof. You kind of switch which field you're working over, and everything works out okay. Okay, so I don't know if it was the smartest thing to answer that question in full detail, but that is the answer. Let me know if you want to ask any other questions.
Looks like that's it for now.
Great, okay. Yeah, so everything boils down to taking your snark verifier and turning it into a circuit so that you can then apply a snark to prove a satisfying assignment for that circuit. And this different scalar field versus base field just makes that a headache. But if you chew enough glass, there's typically a way around the headache without totally ruining your performance. But it can be very painful. Okay, so coming back to Marlin. Yeah, so this is what the verifier needs to learn now to do its kind of final check in Marlin. It needs to learn a sum over all columns J of here we're indexing columns by roots of unity of a hat of r prime comma j times z hat of j. Okay, and so there's basically with quotienting, but given how long we're 90 minutes in, I might want to wave my hands a bit. So with quotienting, there's a way to do this. So there's a way for the prover to provably provide this quantity sum over columns j of a hat of r prime comma j times z hat of j. Let me think about this for a second. I'm just trying to think because I didn't actually load this into memory before today. So I let me just see if I can remind myself how this works in a second, or otherwise I might just wave my hands and tell you that quotienting kind of works exactly as before. So let me just see for a second. Yeah. Okay. I think okay. So yeah, this is a little bit annoying. Sorry, I didn't load it. I forgot that I needed to load this in the memory. That it's a little more complicated to get to the quotienting for this check. Good. So Q, the sum is 0. This is degree 2n. All right, I'm going to give this 20 more seconds. Degree 2n. Okay. All right. Let me do this. I'm going to do a little bit of gymnastics. So, if the prover says, "Hey, I claim that this sum equals some value," I don't know. Let me call it little v. Okay, that's the same as claiming that the sum, which I'll just write out again, sum over j and h of a hat r prime comma j times z hat of j, that sum minus size of h inverse times size of h inverse times v equals 0. Do I want that in the sum or out of the? I think in the sum, something like that. So this is just sort of some gymnastics for convenience. Yeah. So if every one of the h terms of sum gives you v, gives you h inverse v, then the whole sum kind of cancels out the h inverse, and you just get v. And so that's just a little algebra. And then let me call this polynomial. Let me call this thing this thing that we're summing over, everything in here. The text calls this q of j. Now this is a little confusing because this q is before was a quotient. I think that was a deliberate. I think as we eventually get to replacing this claim with a quotienting thing, this is indeed turns out to be the quotient. So anyway, let me just call it q, and hopefully it's not too confusing right now that this is not any kind of quotient. And so so now that the claim after this little algebra is that the sum over j and h, q of j is 0. Okay, and there's something I don't want to. There's a fact that I don't want to prove, but that which is that this sum, okay, is I really hope I don't screw this up. Okay, I am going to wave my hands just a little so that we keep this streamlined. So let's imagine for a second that imagine that Q had degree m rather than 2m. Okay. So, unfortunately, it's a nuisance, but Q is a product of something of degree M and J and another thing of degree M and J. Imagine for a second that it was only degree M rather than 2M. Okay. Then the sum over J in this, mth root to unity, which is of Q of J, would be the same as Q of 0. Okay. And this is always, so I'll call this an exercise that involves a little bit of groups theory. You can read it in the book if you'd like. It's effectively, exercise involves a smidge of group theory. I think it's basically fact 10.1 in slightly different form. Maybe it's Q of 0 times capital H. I forget. There might be some scaling factor. But I think of it as a univariate analog of a certain fact. I'm much more, I like multilinear things. So this is a univariate analog of the following fact, which I think I've mentioned before. So if P is a multilinear polynomial, then summing up P's evaluations over the hypercube, let's say it's a multilinear n-variate polynomial, then summing up P's evaluations over the hypercube is the same as 2 to the n, so there should be a scaling factor here. This is the analogous thing here, times P of 1/2, 1/2, 1/2, just the P evaluated at a single point. Okay, and you should think of this as basically like a half, all coordinates being a half, it's like a center of mass of what's being summed over. We're summing over 0, 1 to the n. And so what point is sort of like right in the middle of 0, 1 to the n? It's like a half in every coordinate. And, this is just a scaling factor. And, the way I see that this holds for multilinear things is right, like I can write any multilinear polynomial by multilinear Lagrange interpolation, right? It's like, some coefficient times, the product of all the variables, because that is one of the Lagrange basis coefficients, plus some other coefficient times like 1 minus x1 times a product of the rest of the variables, maybe the last Lagrange basis coefficient. The last Lagrange polynomial we'll deal with is 1 minus each of the variables. And so for each and every one of these terms, if you plug in a half everywhere for every coordinate, for every single term, you get 1/2 to the n. If you plug in a half for every coordinate, and so P, so P of a half everywhere, turns into if I multiply by 2 to the n, what you just get is the sum of all evaluations over 0, 1 to the n, just because in Lagrange basis, these coefficients here are evaluations. Okay, and so this is the exact same thing going on, which is if Q is sort of just as in sum check, you were summing over 2 to the n Boolean terms, and sort of the lowest degree things that you have control over their values over this interpolating set, are multilinear, degree 1 in each variable. Similarly, up here, we're summing over, m terms, and the lowest degree thing, if you interpolate over the set, is degree m. So if Q were to have the lowest possible, degree m, right, then this sum is just sort of a single evaluation of Q at the center of mass. So this 0 here is just the center of mass of the root to unity, right? They have a ton of symmetry, so kind of, in the complex numbers, right, the roots of unity are like evenly spaced around the circle. and sort of the center of mass is just the center of the circle, which is just 0. So this is like a finite field analog of that. So 0 is like the center of mass for H, and this whole sum of Q's evaluations over H is just the center of mass times some scaling factor, the number of terms in the sum. That's if Q is of maximally low degree. Okay, now this Q, the Q that actually arises in Marlin, is not of maximally low degree. It has degree 2m rather than m. Okay, so if it were of maximally low degree, like we could compute this sum just by evaluating Q of 0. And evaluating Q of 0 would entail, remember Q here is like a hat of r comma j times z hat j. So evaluating Q at the single point 0, it's enough to evaluate a hat at one point, a hat r prime comma 0, and z hat at 1.0. And so, yeah, so, again, if we sort of pretended for a moment that the degree of, this thing being summed is m rather than 2m, then proving that the sum is indeed 0, it would be enough to just get a single evaluation of z hat, which would come from the commitment to z hat. Okay, and then of course the verifier would also need an evaluation of a hat, which I will address in a second. Okay, now there is this complication, which is that this Q thing here, a hat of r comma j times z hat of j is not degree m. Okay, and so computing the sum is not equivalent to just evaluating Q at a single point. Okay, but that you deal with similarly to how we had a quotient polynomial before. So actually, it's pretty. I shouldn't have called this Q. I guess it's not really a quotient. It's the next thing's a quotient. So there's like so the fact is that even though the Q we're dealing with here has degree 2m and not m, something similar holds. Like there exists, I'll call it little h of t of degree m, such that I'm probably going to get this statement wrong. Let me see if I can do it real quickly. So yeah, it'll be like sum over t in h of q of t equals 0 if and only if like q of t is like h of t times the vanishing polynomial for the root to unity minus something else. Yeah, so I'll skip the details, but basically what the prover winds up KZG committing to this H. The verifier, as usual, picks a random point, r prime prime from the field, and is going to check that Q of r prime prime equals H of r prime prime times the vanishing polynomial at r prime prime, minus, something. Yeah, I'll leave it at that. And so, there's there's a song and dance where, like, if Q was really, degree m instead of 2m, we would directly be able to check that the sum is 0, but with one evaluation of Q. But since Q has degree 2m rather than m, the prover has to commit to some extra degree m thing, and that kind of thereby, again, makes everything work out, that we can check that this sum is 0 ultimately with a single evaluation of Q, as well as of the new fresh committed thing and the vanishing polynomial and so forth. So apologies I didn't sort of bring in the memory, the song and dance to turn this second check that the Marlin verifier does into quotienting, but hopefully you got the gist and the hand waving isn't too disappointing. So that, I guess, is basically it. Up to one last technical issue. So let me just summarize the protocol. Right. So the prover commits to, at the very start, to little a hat, little b hat, little c hat, and z hat. To do the first check, that a hat I times b hat I equals c hat I for all I and h, the prover also commits to Q such that a hat times b hat minus c hat equals Q times the vanishing polynomial. And then this equality, the verifier checks at a random point, which, basically it can do with a single evaluation query to each of the committed polynomials, Q, a hat, b hat, c hat. And then to check that, like A in fact equals AZ, B in fact equals BZ, C in fact equals CZ. The verifier picks an R prime at random, and needs to basically check, that like a hat of R prime equals this weird sum over columns of a hat, big A hat now, of R prime comma J times Z hat J. And then this quantity can be computed with, via something similar to quotienting. So P commits to, some univariate H and does a check, that looks a lot like this sort of check from up here. Be sketchy with the details and leave it at that. And so then so this check that I'm hand waving a little bit needs the verifier to evaluate a hat at a random point and z hat at a random point. And again, z hat can just come from the KZG commitment to z hat from the very start. And then here we have a real issue. Okay, so in Spartan last week, right? Remember, the verifier needed something analogous, a twiddle, where this was the multilinear extension of A at a random point. Okay, and what I said there was, if a twiddle has repeated structure, or A has repeated structure, which is like almost always the case in practice, typically the verifier can then compute this evaluation, any evaluation of a twiddle quickly on its own in log, constraint size time. Okay, I think that will basically never be the case for a hat when you deal with univariate polynomials. Okay, so another thing, so it's just univariate polynomials don't seem to be quickly evaluable, even when there is repeated structure in the vector they are extending. So another thing I said, so this just has no analogy. This thing from yesterday just has no analogy today. But another thing I said from yesterday was in the event, which I think basically almost never arises in practice, but like if a twiddle cannot be evaluated, at a point r prime in really quickly in log m time. What I said was an honest party can commit to a twiddle in pre-processing using a polynomial commitment scheme, and then later provide an evaluation proof in the online phase once the verifier says, hey, I need to know the committed polynomial at r prime comma r prime prime. The untrusted prover now, and later the untrusted prover can reveal a twiddle of r prime comma r prime prime. It needs to, because the prover is untrusted, it needs to provide an evaluation proof. So that's what happens in Marlin. Okay, Marlin basically has no choice but to do this, even if there is repeated structure in the constraints. Again, because when you take the univariate or bivariate low degree extension of something structured, you do not seem to get something quickly evaluable, whereas typically the multilinear extensions are. Now there is an annoying complication, which is typically these constraint matrices A, B, and C are sparse, meaning they have m by n entries, one per row column pair, but typically only order n plus n of them are non-zero. Okay, and that means it's not trivial. When I say have an honest party commit to them in pre-processing, and then the prover can provide the needed evaluation on the fly with an evaluation proof, it's not trivial to ensure that pre-processing, so getting that commitment computed, plus computing the evaluation proof by the untrusted prover on the online phase, it's not trivial to ensure that all of that takes time, order n plus n, meaning the number of non-zeros in these matrices, NNZ is for number of non-zeros, rather than m times n. So achieving that is called, if you do achieve it, it's called a sparse polynomial commitment scheme. Okay, and last week I was comfortable just telling you, hey, like in almost all applications, that seem to arise in practice, these constraints have repeated structure. It's the same simple constraint kind of over and over again. And so the verifier will evaluate the, multilinear extension of the constraints quickly on its own. And like, don't worry about, this pre-processing stuff. You just won't need to do it. But today you really have no choice but to do the pre-processing. There's maybe been some work to address that. But anyway, you would have to do a whole bunch of extra, snark design work to get around this issue. So I feel like I should tell you a little bit about these sparse polynomial commitments. But basically, I'd say like the most complicated part of both Spartan and Marlin is the sparse polynomial commitment. And then in practice, I'd say for Spartan, we don't even really use it. But for Marlin, you really kind of have no choice. So I'm just going to sketch it, which is the following. So, these matrices A, B, and C that are sparse, they have m times n entries, but there's only like, m plus n that are non-zero. What you can do is you can write down what I call a densified representation of them. Okay, so what I mean is, for like, let's just focus on A. So for A, what we'll do is we'll write down, for each row, like a list of the non-zero entry, like of which entries in that row are non-zero. And, and the value of those entries. So that's sort of like two vectors. Like one is a vector of indices, like which indices in this row are non-zero, and one is a vector of values. And there's sort of, let's say these, like every single constraint involves only, like a one or two non-zeros or something, then like, these two vectors will have, maybe like one or two entries, per row. So these vectors will live in like field to the 2m or something. Of course there'll be one of so you'll get like two vectors in field to the 2m for each of the three matrices. So in the end you have like 12m values getting committed. But yeah, so basically what's going on is in these sparse polynomial commitment schemes, the prover will commit to these vectors. Right. So, again, like you have these matrices, they're sparse, they have m times n entries, but only like 3 entries, 1, 2, 3 entries per row are non-zero. So what the prover is actually going to commit to is not like the sparse matrices themselves, but rather to a description of the matrices that just lists which entries are non-zero and what those entries are. Okay. And that's the commitment. Okay, so I shouldn't say P, I should say the honest party that's doing the pre-processing. Okay, and then in the online phase, when the untrusted prover needs to produce an evaluation proof, like a hat or a twiddle of r prime comma r prime prime, what it proves is it proves it correctly ran an algorithm that takes as input the densified representation that it committed to. So that takes as input the committed vectors. Which is just the densified description, like the list of all the non-zeros. And the values of those entries. And correctly, from that input, computes the requested evaluation. Okay, and basically these algorithms, so it's basically a sparse polynomial evaluation algorithm. It's like you're feeding into the algorithm like the non-zero coefficients of the sparse polynomial or something like that. And the algorithm is trying as quickly as possible to compute this particular, to evaluate, that sparse polynomial on this particular point. Okay, and these sparse polynomial evaluation algorithms, they're like really, really simple and efficient. And so it turns out to be pretty straightforward to prove that the prover ran that algorithm correctly. So, these sparse polynomial commitment schemes, Marlin's is called Spark. Marlin's doesn't have a name. It's just a sparse polynomial commitment scheme given in Marlin. They look nothing like, a ZKVM or something. They look nothing like I ran this RISC-V program correctly. They're proving they ran a very specific algorithm that takes as input the non-zero coefficients of a sparse polynomial and evaluates that polynomial at a random point. That algorithm is very specific and simple. And so you can give like a pretty clean, straightforward snark for proving you ran that algorithm correctly. And as a result, like the committed vector is, the prover's committing, and the prover, the honest party, commits to, like basically, some constant multiple times number of non-zero field elements, number of non-zeros in the matrices field elements or something. And then the evaluation proofs turn out also to involve committing to roughly that many field elements. I'm making up 3 here. I don't know what the leading constant actually is. I'd have to think very carefully. Basically, because the runtime of this algorithm that takes as input like the non-zero coefficients of the sparse polynomial and spits out the requested evaluation, like it spends like constant time per non-zero coefficient. So like intuitively, if the simple algorithm runs for t steps, you should be able to kind of just prove you ran it correctly by committing to a couple of group elements or field elements per step of the algorithm. So that's how these sparse polynomial commitment schemes work. And the details I'll leave for a later session. The same details go into lookup arguments and things like that, basically because this sparse polynomial evaluation algorithm is just computing a lookup table and doing lookups into that table. So I'll treat it as a black box right now, just to give you a sense of how these sparse polynomial commitment schemes work. But yeah, just to, I think the high level point though, this is one more benefit of some check-based snarks, is they sort of, they kind of have 2 modes where if you are running them on something with repeated structure, you typically don't need to have these sparse polynomial commitments. But if you, because the verifier can evaluate, like the polynomial, the multilinear polynomials capturing the constraint system, like in logarithmic time and the size of the constraint system. But if you use univariate polynomials, it's like not really, so clear or easy to do that. And so you either need to work much harder to get a very, very, very specific kind of structure in there, which is kind of what Starks do. Or you need to be prepared to run something like a sparse polynomial commitment scheme, which, how those work, I just sketched for you today. And that's basically what something like Marlin, and implicitly, if you squint enough, Planck and Gross 16 wind up doing something a little bit similar as well. That's what they wind up doing. Okay, so that's Marlin. Univariatization, if you will, of Spartan. Similarly, Spartan is sort of a sum-checkization of Marlin. I hope the comparison was understandable, and apologies for all the rambling. I will take any final questions, and otherwise, that's it for today. Questions?
I only see one question, and it is, how does knowledge extraction work here?
Yeah, great. So I'm going to be sketchy. In fact, I have heard that if you look at, I've heard from some of the Marlin authors that there might even be like little issues with like the Marlin knowledge soundness analysis in the paper. So, so I will be sketchy, but like high level, it's very, very simple. Okay. Which is KZG commitments, under appropriate cryptographic assumptions are extractable. And that statement does a lot of work. So if you just believe me, so what that means is like, if, anyone, if a prover, commits to some polynomial, like a hat, so it sends, like a C, which is supposed to be a commitment to some univariate polynomial degree M, and, is prepared to answer, any evaluation queries for the commitment, that is like open the commitment, to, some, to, convince the verifier that, in fact, A had evaluated at some point of the verifier's request equals some value of the, the proof's claiming, that means you can actually know a univariate polynomial of, the claim degree inside the commitment, like the prover, so basically, if I give you, if I give you KZG commitments to polynomial, like or in Marlin, several polynomials, like 10 different polynomials, and the prover is capable of answering evaluation queries for this committed polynomial, and is doing like almost all the work of knowledge extraction for something like Marlin. Okay, because once I extract, get out of the prover's head, A hat, B hat, C hat, Z hat, and all these quotients that came up. Okay, well, verify times Z equals B, and C equals C times Z, right? These checks are like, A hat R times B hat R minus C hat R equals Q of R times the vanishing polynomial at R. Like this check is enough to guarantee that this holds stuff. So basically, like, and this is how to think about knowledge extraction for like basically all snarks. It's like the prover commits to a bunch of stuff. The commitment schemes are always like extractable. So, and like most of the, pain of establishing knowledge soundness is like, really just showing the commitment schemes are extractable. So you pull, like the vectors inside the commitments, like out of the prover's head, because those are extractable commitment schemes. And then everything else the prover does is in the PIOP, the polynomial IOP. And that PIOP is explicitly designed to confirm that the committed vectors satisfy certain properties that, together guarantee that there's actually a valid witness in there. And so that's what would happen here. So you just, you figure out what polynomials are inside the commitments, and then the extra checks done in Marlin, which are, it's really can be formalized as the PIOP within Marlin, is doing randomized checks to guarantee that those vectors themselves like act as a witness for the prover's claim. Does that make some sense? Was that a helpful response?
He has not replied, but it makes sense to me.
Okay, great.
He said, yep, cool. Shall we stop there?
We're good? No more questions?
Correct.
Okay, wonderful. Well, thanks as always. Extra long session today, so I keep getting worse. I think we'll next time probably start with going into zero knowledge and then Sigma protocols, and from there we build polynomial commitment schemes. But maybe Abhi and I need to chat to just confirm that that's a good plan. Anyway, next week I'm traveling, so it'll be an off week. I'll write that in the chat right now. But then my travels are done for a while, so we'll be back 2 weeks from now. So I will see you hopefully 2 weeks from now.